Hi, I am Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. Today I am going to explain about binary codes. What is the use of binary codes in digital computer? Generally, in digital computers, the operation of all operators performed using binary information. When it performs in binary information of a given any digits, numbers, alphabetical letters, these numbers are directly converted into binary information is the one way to represent. And another way is those binary numbers also represented in binary codes. Here, that binary codes, for example, a digit 9 can be represented in actual binary conversion based on the weighted form and based on the binary codes. The main characteristics of a weighted code is each binary bit is assigned by a weights. Let us take this binary representation of 9. 1, 2, 4, 8 code weights. So 16. So we have 9 means 8, 1, remaining will be 0. Here, for example, if I am putting 19, what is the binary representation for 19? 16 plus 3, 0, 0, 1, 1. So we get 19. This number is also can be represented in the form of binary words in digital computers. Each digit represented with its binary codes. So these two ways to represent in digital computers. So these binary codes, one way is weighted code, another one is non-weighted codes. What is weighted binary codes? Weighted binary codes are those which follow the positional weighting principles, in which each position of the number represented a specific weight. For example, start from LSB, the first bit or first digit represented with a weights. In binary representation, first LSB bit represented by 2 power 0, and next bit is 2 power 1, and next bit is 2 power 3, likewise. So actual representation of binary number of 19, how we can write this 16, 8, 4, 2, 1 code, 16 and under 16, 1, 0, 0, 1, 1, 1. But this number goes on increasing by number increases in representation. So here also there are another binary codes which can be divided into two parts: weighted binary code and non-weighted codes. This weighted binary codes having specific weight. For example, BCD, binary coded decimal number. Binary coded decimal having weights 8, 4, 2, 1. The MSB weight is 8, LSB weight is 1. Similarly, 8, 4, minus 2, minus 1 also a weighted binary code. And 2, 4, 2, 1, 5, 0, 4, 3, 2, 1, 0. These are the examples of binary weighted codes. And non-weighted codes are the codes which are not placed any weights, not placed any weighted in the codes. It means that each position within the binary number is not assigned a fixed value. It may be some other value. The examples of non-weighted codes are XS3 code and gray codes. Now let us see one by one what are the weighted codes and non-weighted codes and what is their properties. If you see here, this table which gives the conversion from decimal number into its weighted and non-weighted codes. First we will see that some weighted codes like BCD and 84 minus 2 minus 1 and 2421 and last binary code. Here the decimal numbers 0 to 9 can be represented in BCD code. BCD code follows 8421 weight. The LSB bit having 2 power 0 nothing but 1, next bit 2 power 1 nothing but 2, next bit 2 power 2 nothing but 4, next bit is 8 2 power 3. So only each digit represented with 4 weights 8421. So we can represent any number. For example, it is a 8421 code. If I want to represent 3, if I want to represent 3, by following this code, we can make this 2 and 1. 2 plus 1 will get 3. So that 4 weight is 0. 8 weight corresponding bit. The bit corresponding to weight 8 is 0. This one is 0. 0 0 1 1. So we can make this 3 is a 0 0 1 1. Likewise, we can take the 0 as a 0 0 0 0 and 1 is 0 0 1 and 2 is 0 0 0 1 0 and 3 is 0 0 1 1 and 4 is 0 1 0 0. When we see this second column, it is similar to normal binary to decimal to binary conversion. But when we, as soon as the number lies between 0 to 9, when it is exceed that number 9 greater than 9, then it fails to represent normal binary representation with the BCD. So normal binary representation which consists of more than 4 bits, and in BCD we can only represent a 0 between 0 to 9. If more than 9 number can be treated as in the BCD is different individual digits. For example, if I am take the decimal number 10 or any number 10, so we can represent this 10 in normal binary representation is 1010, but in under BCD, if you take this one 8421 code, so if BCD, each digit we cannot call it as 10, we can call it as a 0 and 1 and 0. So it has some individual 8421 code, it has some individual 8421 code. Next one is 84 minus 2 minus 1. This is also called weighted code. In this, the weights are called 8, 4, minus 2, minus 1. But based on this code, we can represent these decimal numbers. We can represent these decimal numbers. Let us see here. 0 can be represented by all zeros, and 1 can be represented by, how can we make this 1? By combining 4 minus 2 minus 1. 4 minus 2 minus 1 means 4 minus 3, you will get 1. So that's why we use, to make this 2, we use 3 weights. One is 4, another one is minus 2 minus 1, so that we can make the number 0 111. And number 2, decimal number 2 means we can collect the 4 and minus 2. 4 minus 2 will get 2. That's why we need one weight is 4, another weight is minus 2. So that number is converted to 0 110. 3 means 0 101 means 4 minus 1. We can take 4 and minus 1 weights. So 0 101. It is for 3. And 4 means directly we have a 4. So we take 0 100. So likewise we goes on increasing the number, that number representation based on the 84 minus 2 minus 1. What about 9? So for example, if you see 9 means 8 4. If you 8 4 12, total is 12. 12 minus 2 minus 1. 12 minus 3 will get 9. So that we will take 4 ones. in this 8421 codes. And a 2421 code, in this 2421 code, we follow the 2421. Here it is 2 times 2 occurred, but we'll take that left side last MSB bit 2 considered for upper digits, and this lower 2 considered in for lower digits. 0 can be represented in all cases, all 4 zeros. 1 can be represented, we have already directly available in 1, so 0 0 0 1, and 2 is also available, but which 2 you can choose means first 5 digits can be represented with represented by considering the second this 2, and next 5 bits considered to make the number is this 2. So for example, if you take this 2 means already lower bit, this 2 is there, consider that 2 1, remaining will be 0, remaining bits will be 0. And then 3 means consider this 1 and 2 lower bits, lower digits, so 0 0 1 1. 4 means number is already available, 0 1 0 0. Likewise, we can make the number 9. 9 can be represented with 2 plus 4 6, 6 plus 2 8, 8 plus 1 9. So we can make all ones. So these 8421, 2421 are and XS3 code, they are self complements. Self complement numbers. So this property, because of this property, these weighted codes create like 84 minus 84 minus 2 minus 1 2 4 2 1. Here the last column, bicquinary code 5043210. This is one of the best code to detect the errors. While transmitting a bit from transmitter to receiver, at the receiver end, by using this code, we can detect the errors. This is the basic representation. In this bicquinary code, there are 2 zeros. One is this one, another 0 is this one. What is the purpose of these 2 zeros? If you see, to represent this decimal number 0, there are 2 zeros, so corresponding 2 zeros under 2 0 we can make this ones. So 0 1, 4 zeros 1 to represent 0. And 1 we can represent. So here already we have 1, so under 1 we can make this one. And this MSP side there is a 1 0, make that 0 1, so that it won't change, the number won't change. So what will be the weights multiplied this binary number? 0 into 0, 1 into 1 1, and everything will be zeros. This 0 into 1 0, so the number should be called as 1 only. And what is the purpose of to make the extra 1 under 0 means, if you observe the entire sequence, the numbers from 0 to 9 of these bicquinary codes, each digit represented with 2 binary numbers. If you check any number which consists of 2 ones, when it is represented with the 2 ones, so when a number, if you send for example 8 9, what is the corresponding 8 bit? 8 is nothing but 1 0 0 and 1 0 0. 9 means 1 0 1 0 0 0 0. If you see this number having 2 ones, this number having 2 ones, based on bicquinary code, if you send 89 number through a channel, so at the receiver end, each package, this is one package, this is another frame or package, this frame consists of 2 ones, this frame consists of 2 ones. Whenever any receiver end which consists of more than 1 or less than 1, less than number of ones 2, number of ones are is equal to or less than or equal to 2, or less than or greater than 2, then there will be an error. For example, this bit is changed to 0 to 1, the number of bits are 3, so it will be error occurred in the output. That is a purpose, that is the property of this last bit binary code. In order to make that digits 0 to 9, each number consists of 2 ones, so that the code prepared like this 5 4 3 2 1 with the put zeros here and 0 here, so that we can create 0 to 9 digits with 2 logic ones, logic symbol, logic level symbol 1. 2 logic ones must be there in each and every digit. And what is the purpose of 8421 and 84 minus 2 minus 1, 84 2421? These weighted codes, based on these self complements, we can use in computers, digital computers. And next example is XS3 code. These are the example for non-weighted codes. XS3 code and gray codes. So take this XS3 code. What is XS3 code? Why it is called non-weighted code? XS3 code means XS3 code means which is equal to BCD code or 8421 code plus 3 in decimal representation, 3 in decimal representation, or BCD in binary 8421 code, 8421 code plus 0011. When we add 3 for all the numbers, we will get XS3 code. Let us check one by one. What is the XS3 code? When I'm asking you what is the XS3 code for 9 in decimal, then you can see, you probably say that the XS3 code is 12. When I'm asking what is XS3 for 2, decimal number 2, then automatically we'll say that the XS3 code is 5. But we can represent it in binary. What is XS3 code for 0010? It is number 2. So just we can add 0011 for each number. So here it is a 2 in binary, 2 in binary 0010. Just we can add, like add 3. So that is the XS3 code for 2. 1 0 plus 1 1, 1 plus 1 0 1 carry, and 1 0. This is represented in decimal number is 5. So what is the XS3 code for 2 is 00101. So XS3 code for 2 is 0101. What is XS3 code for 6? 6 means 0110 in binary. XS3 we can just add 0011. We can get the 6 plus 3 9. 1011 is the XS3 code. If you check this column, each and every number start from 0 to 9. Whatever the number converted into XS3, which has no weights in each bit. When compare with BCD, it has 8, 4, 2, 1 weights are there. But in XS3, when we add a constant number, 3 is added to a code, weighted code. In XS3, it will become as a non-weighted code. So if you check any number 9, for example, 9 XS3 code for 9 is 1100. So there will be no code for each digit. Each digit, it doesn't follow any codes. That's why it's called XS3 code is called non-weighted codes. This is the table which explains about the difference between the BCD and XS3. Here it is 0, 4 zeros, and BCD plus 0011. You will get a XS3 code. 0 plus 3, 3. It will start from 3. So when it is start from 3, 1 plus 3, it is 4. It is 5. It is 6. So 5, 0, 101 plus 3 will get 8. 1000 represents the 8. So this is the XS3 code. Now another example for non-weighted codes, which is example for non-weighted code is gray code. And what is gray code here? The gray code is nothing but it is a conversion from, like gray code representation is, which consists of single bit change from the neighboring number. When we see this the gray code and binary code, what is the difference between gray code and binary code? If any given binary code, how to convert that gray codes? So here it is a simple example for conversion of a given number binary to gray code. So the number is 1010 110 in base 2 converted to gray codes. Take the number as it is 10110. So here what happened? The MSB bit, this MSB bit of binary number, this is the binary sequence 1 0 1 1 0. This is the binary number. Take the MSB bit as it is. Take the MSB bit as it is in to convert from binary to gray. Take the MSB bit as it is. And this number as it is. And if you want to get the next number, XOR operation with this MSB bit and the next MSB bit minus 1. Next bit. Diminished MSB bit. So when we perform the XOR operation, you will get the second bit in the gray code. What is XOR operation? If we see here the table, any two bits 00, 01, 10, 11. What is the XOR operation? If for example it is a bit A, a bit B, what is XOR operation? A XOR B, 0 XOR 0. If both inputs are equal, both inputs are same, the output will be 0. If both the inputs are up, like 0 and 1 and 1 and 0, opposite inputs, you will get 1. Same inputs will get a low output, opposite inputs will get high output. So 0 1 1 1 0 1, remaining case 0. So here what is the MSB bit is 1 and the next bit is diminished MSB is 0. XOR operation with 0 and 1 is will get 1. Next, in order to get this number, XOR operation with this 0 with the next third number. So that number 0 XOR with 1 will get 1. In order to get this number, XOR operation with this number and next number, the XOR operation for 1 and 1 is 0. And next, if you want to get this number, XOR operation with this number with the last number. So 1 0 will get 1. So in this way we can get this number is 0 1 0 1 1 0 1 is the gray code for a given binary number. This is the binary number, this is the gray code number. The mathematical equation for this gray code number is, for example, that binary number representation. It is a binary number for a 5-bit representation. Start from MSB bit is B4, B3, B2, B1 and B0. So this B4 take as it is for to get the gray code G4. So that's why I am taking how to get this G4 is equal to same B4 bit. And what about G3? How can we get G3? This G3 can we get from the operation, XOR operation between B4 and B3. B4 and XOR operation with the B3. So on right side, in binary to gray conversion, the left side equation we need to get that gray. Right side only take the binary, no other bits. Here that G2 we get G2 from B3 XOR operation with B2. So we will take B3 XOR operation with B2. G1 can get, this is G2, you will get G2. And how can we get G1? XOR operation B2 with B1. So B2 with B1. And last one is Z0 is equal to B1 XOR operation with B0. B1 XOR operation with B0. We'll get G0. In general case, what is the equation for G suffix I is equal to, this is the number, this is Gi, Bi. Next, this is I minus 1, will get Bi XOR operation with, Bi XOR with Bi minus 1. When we substitute in the I, 4, we can get that this equation and this equation will get these 5 gray code equations. So that we will convert binary to gray code. What is the main property of this gray code? When we see this gray code, this table, for example, if you take this gray code, first we'll see gray to binary conversion. Similarly, suppose in the problem given gray code and you will get convert to binary. Here it is given the number is 1010 is the gray code, and how to convert this gray code into binary conversion. Here it is somewhat different than binary to gray code. So gray code to binary, how can we take? Take the gray code number with a coefficient represented with G of 3, G of 2, G of 1, G of 0. And this binary number, how to get B3? Take the G3 number as it is. And how to get the second number in binary? B2, B of 2. So B2 can be obtained from B3 XOR with G2, diminished MSB bit of gray code with B3. B and G XOR operation. You will get B2. Similarly, in order to get this B of 1, XOR operation of this recently getting binary number with G1. And next B0, B of 0 will get recent binary number B1 and G0. You will get XOR operation, you will get B0. So what is the mathematical equation for this binary? So we have a gray code numbers and we will get binary numbers. What is the first one is B of 3, getting directly from G of 3. So direct conversion. And to get B of 2, XOR operation of B3, this B3 and G2. So B2 is equal to B3 plus B3 XOR G2. B1 is equal to B2 XOR G1. B0 is equal to B1 XOR G0. So here we can right side we can use gray code given binary gray code number and the previous binary number we got. If you see an example here, in this example, what is the gray code number? Gray code number is 1010. Take the 1 as it is, you will get 1 in the binary. It is gray. It is binary code we need to find out. Take this number as it is. Next, the XOR operation with this number, XOR operation with this number and this number and G2. So what is the XOR operation with this number? 10. You will get the answer. 10 XOR is 1. Similarly, this one XOR with this one, and B2 and XOR with G2, you will get B1, XOR number is 0. And this number XOR with this number, you will get 0. So our binary number is 1100 for given number 1010. So in order to get this gray code to binary and binary to gray code, if you see any given binary number, for example 9 is nothing but 1001. This is a weighted code. If you convert to gray code, so take the gray code 1 0 XOR operation with 1, XOR operation with 0, XOR operation 1. This number having, it does not have any weight. This number having weight, given binary number. That gray code does not having any weights. That's why gray code is non-weighted codes. And if you see this table, we have a 10 decimal numbers. When we convert that decimal number into gray code, whenever gray code operation, what is its corresponding gray value is by seeing this table. So if you create this table to get BCD and its corresponding gray code, 0 BCD follow the 1248 code, 1248 code, but gray does not have any code. So but when we convert by following the procedure which I had explained, 0 4 zeros in BCD, 4 zeros in gray code, 1 0 0 0 0 1 in gray code, again 0 0 1 by following the procedure. What is the property that gray code had? The gray code property is when we see one number with the other number, one gray code with the other gray code number, only one bit change. We find one bit change in the given table. So 4 zeros, the next number is 0001. So 3 zeros are constant, only one bit changes, 0 to 1. Similarly, if you check 1 and 2, so here 2 zeros are common and 1 is also common, only one bit changes. This kind of property will make use of this gray code in Karnaugh maps to minimize our realization of a given Boolean function. So we will, when it come across that Boolean functions, minimized Boolean function using K-map, we will use this kind of gray code, because whenever any two numbers, for example x, a variable, if let us take a variable xy plus xy bar. So here we can make a one variable change. X is common and y change with y bar. So in this case we can take that x common, y plus y bar. In Boolean algebra it will be equal to 1, so that we can minimize the Boolean function. Why we can minimize the Boolean function? In Boolean function y plus y bar is equal to 1, so that when x into 1 is nothing but x. This kind of 4 variable expression can be minimized into x. So all these Boolean variables and Boolean postulates and formulas we'll see in future class. So here that kind of common variables are there, then we can minimize it. Here also this binary number, whenever 3 bits are common, 1 bit is changed, take that common bits and that complement bits, that 0 and 1 changing bit will be gets reduced. So if you see any number, if you see here 8 and 9, so this 1 and 1 are common, 1 and first all 3 bits are common, only 1 bit change. This property will make that use in Karnaugh map. When you use this table, this is called weighted code, this is called non-weighted codes, this is called weighted code, weighted codes, weighted codes. And if it is meant to add with this table gray code, the gray code is also non-weighted code. So what are all the weighted code and what are all the non-weighted codes which are useful in the digital computer operation, performing the operation? If we represent this one of the BCD code, what is its property? Let us take one of the weighted code property. What is the main purpose of BCD? The binary code decimal. Binary code decimal means whatever the given decimal number, each digit can be represented with the 8421 code. So in this case, when we represent 25 in BCD, we can call it as 2 and 5. 2 can be represented with 0, 0, 1, 0, and 5 can be represented with 0, 1, 0, 1 based on 8421 code. So this kind of information transfer associated with this 25 or 25. If we call 25, call it as a 25, our code is, actual code is 1 0 0 0 1. 16 plus 8, 24 plus 1, 25. This is actual binary number, but this is a BCD number. So computer can choose based on the application to send the message 25 can by using 11001 or by using BCD code. For we can use 8 bits. Here we can use 5 bits. Here we can use 8 bits. Among 8, 4 bit for 2 bit 2 and 4 bits for digit 5. So whenever we represent any number more than 9, we must ensure that a number is converted into BCD. Whenever that number is greater than 9, if it is greater than 9, and then we can add 6, then we will get 16. And what is the binary number for 16 is 1. 6 means 16, 1, 4 zeros. So if you represent this number separate 4 zeros, 0 means it is 0, 1 means we can take it as 1. So when we make this 3 zeros before 1, it is treated as 1, it will be treated as 0, 1 and 0. So in order to make any decimal number more than 9, and to get the BCD number, just we can add this 6. This property of BCD number will make each digit can be represented with the 8421 code. Sometimes we have to we need to addition with this BCD, addition of 2 BCD numbers. So when addition of 2 BCD numbers, we must follow this 8421 code. For example, a BCD number 25, another BCD number 25. So whenever add these BCD numbers, 5 plus 5 will get a 10, but it violates the representation of BCD. Only BCD numbers represented within 0 to 9. So in order to this get 10 to BCD number, add 6, so that we can 1 and 0, that 0 become here and 1 here. So we can add 2 plus 2 plus 1, 5. So this 5 and 0 is the BCD answer. Not directly simply adding. We can make this number into BCD number. So when we performing some operations like addition and subtraction, if you see this addition, subtraction has been done by using complements in the computers. If you take any two numbers, 1010, 1101, when we add these two numbers, so when we add these two numbers, 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1 is nothing but 0, 1. So this is the end carry, 1, 0. When we perform this operation using the BCD, it is different when this is exceeding this number, so we can add 6 with this number. Likewise, whenever we represent any binary number in computer, which can be represented either way, either a direct binary conversion by using the weighted codes 1, 2, 4, 8, 16, 32, 64, 128 and so on, or otherwise we can use the some of the weighted codes like BCD 84-2-1 and 2421 or 5043-210. And another way, codes is binary code is non-weighted codes, in which this non-weighted code can be converted from binary code to from weighted code. So this XS3 and what are the properties of this weighted codes? That weighted codes property is, so they can be used in digital computer to represent a binary number. And what are the properties of XS3 and gray code is, XS3 code is just excess of any given binary number, and gray code is we can convert that binary to gray code. It will be act as a 1-bit change in the bit frame, and these are useful for useful and considered as non-weighted codes. So any number, any binary, any information travel through the serial communication or any bit streams available in the digital computer, that a bit stream may be represented with directly we can represent it with the direct binary conversion, but mostly we can be represented by using binary codes. Whenever any sequence bit streams or any sequential bits are collecting, that collecting bits may be definitely followed by any binary codes, either weighted codes, most probably weighted codes. So in this way we can take this codes, binary codes, we can use in the digital computers. So in this case we used 8421, 84 -2 -1. That means we can use negative number weights also, used for the weighted codes. With this I'm done with this weighted code. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.